All right, box plot time. So box plot, also known as box and whisker plots. We'll talk about what these are. The good news is when you guys do them, you'll just do them on Google Sheets, and I think it's the best way to get the data as opposed to doing by hand. But you need 6 points from the data. So you need the minimum value, so that's just the lowest value, and then you need the maximum value, which is the highest value. Okay, so that's going to be your top value and your lowest value. There are outliers too. So if outliers are around, we'll deal with those after. And then what you're going to find is the 25th percentile, the median, and the 75th percentile. So go back in the videos and learn how to find those by using Google Sheets. So what those are, if we want to go through them, is the 25th percentile is the value of the guy who is bigger than 25% of the other guys. So if you are a baby that is in the 25th percentile of weight when you're born. So they talk about, if you're wondering why I'm saying babies, they talk about percentiles when they talk about babies all the time. So you can ask your parents about that. They'll give all the data, 25th percentile, 50th percentile, 80th percentile, and that's a ranking. So that baby is bigger than 25% of all babies. The minimum value is the smallest baby. The 25th percentile baby is the guy who is bigger than 25% of the data. So that's called Q1. The median we know is the middle baby. All right, so the middle baby, or the 50th percentile, bigger than 50% of all other babies. The 75th percentile is what we call a Q3. Okay, so Q3 is the 75th percentile, which means that you're bigger than 75% of all babies. And the maximum baby is the biggest baby. Now, there's outliers. We'll talk about that later. But that's what you have. The minimum, Q1, median, Q3. Again, these Google Sheets will give to you. So figure out how to do that. It's not that hard. You get some data. It'll give it to you. When you represent them, you make what's called a box and whisker plot, or a box plot. And how this works is there is your minimum, there is your maximum. Okay, so I like to just start with the extremes here, minimum and maximum. This line here is your Q1. Okay, your 20th percentile goes here. Your median is this thick line in the middle, and then this guy goes here. So if we were to make these by hand, which we won't, but let me just show you how they are generated. What happens is you have your minimum, your maximum, okay? Then you have your median, and then you have your Q1 and your Q3, okay? So min here, and how we draw these is we draw a box around the middle part here, okay? So I have Q1 here, Q1, Q2, or your median, okay? So your median is your Q2 or 50th percentile. Q3 is the 75th percentile. And then what we do is we draw what we call the whiskers. Okay, you can picture this here. There's your box, and then your whiskers that go to your min and your max. So excuse the writing, but that's sorry. We draw a box and whisker plot. Now, they don't always look like this. Okay, sometimes we're going to see some that are going to look like this. Okay, you might see something that even looks like this, or you might see something that looks like this. Okay, and the key to understanding a box and whisker plot is each of these quartiles, the first quartile, the second quartile, the third quartile, and the fourth quartile, that's what we call this, has the same amount of items in it. So if we're looking at babies again, and we had 100 babies, just to make life simple, this would mean that there's 25 babies here, 25 babies here, 25 babies here, and 25 babies here. Okay, so it's not that there's more, and that's the case always. So if this guy is bigger, if I have a distribution of babies weights and it looks like this, there's not more babies in this little piece here. There's still 25 and 25 and 25 and 25. But if I was to put a scale here, and this is 6 pounds, and this is at the end here, we're going to have 9 pounds. Pretend this is 3 different groups of babies. What we're looking at here is, in this situation, the more spread out a box or a whisker is, it means that that quartile of data itself is more spread out. So in this case here, the third quartile, so between 50 and 75%, okay, the babies that are above the median, okay, but not the biggest, they're super spread out. And that's why it looks like this. In this case here, this guy and this guy are spread out. So the smallest babies and the biggest babies, they're more spread out in size. Okay, that's how you get the bigger sizes here. You could even have something like this. They don't even have to be close to the same size. You could have something that looks like this, right? And there's less spread. There's less range in the first place, but there's less spread also. So these would be babies that are very similar in size. All right. So it's not, this is a different thing. When we see graphs, when you see anything, right? When you look at a circle graph and the biggest piece is this guy here, that means there's more. When you see a graph and it goes like this, and this guy, oh, look how tall that guy is, that means there's more. When you see a curve, the tallest part is more. That's different here, okay? When you look at box and whisker plots, it's not bigger, it's more spread out. It's hard sometimes to imagine that, but that's what's going on. So 25% of the data is here, 25% of the data here, 25% of the data is here. So that's what a box plot or box and whisker plot is. Why do they matter? They show you how data is spread out, like I just said. So let me go through some examples here. And I think this is really good how they compare stuff in your notes here. So give me a second here. So we look at this group here. Let's just look at this violent crimes. So here, the violent crime data from the histogram above is negatively skewed. Okay, so we'll talk about that in a second, how that works. But there's two things I want to do. One is to compare box plots themselves. But another thing is to go back to what we were talking about the other day about distribution types. This one here looks to be, there's not one end that is more spread out than the other. So this guy here, if you were to graph this, would be a normal curve. Okay, you got the data in the middle, okay, less spread out, and then the guys on the left and the right are more spread out. And if we were to graph this, you would get what we had as the normal curve before, right? Like a bell-shaped curve. If you were to graph this, what you notice here is this data here is more spread out. It's pulled here. So pulled over, right? You can picture this. Here's your median here, and there's some range over here. There's much more range on this side. That's going to cause what we had last day as a negatively skewed plot. Okay, so that guy here kind of goes, if we go back to what we had a couple in the last video, that here is going to be negatively skewed. It's get pulled to the left. Okay, the box here, if we were to graph this, the median is over here, right? But the side parts are pulled over this way. So if we were to do a box and whisker plot, this guy here, a normal curve, if we had a normal curve, right? Your box and whisker plot, there's your max and your median. The guys, or the max and the min, sorry. Your guys in the middle are going to be less spread out, right? Because the middle data here is less spread out. And you can have something that looks like this. That's a normal curve. Okay? But if this was pulled this way, what you're going to have is your mins pulled over, and everything gets pulled over just slightly. Everything else gets pulled over just slightly. And it will look something like this. Okay? So anything that looks like that with the guy, this whisker longer, is going to be negatively skewed. If the whisker on the right was bigger, okay, so something like this, then you're going to have this sort of thing, positively skewed. Okay, so that's how they relate to each other. The last thing we want to look at is how do specific box and whisker plots relate to each other, and what does that mean? So when you look at this here, and I think this is really neat. So this guy here and this guy here, we're looking at a histogram from 2000 to 2005, and we're going to look at the data difference. And when you look at these two, you can talk about, it looks like there's a little bit more over here than there is over here. But the box and whisker plot can help with that, okay? One, you look at 2000 versus 2005, okay? So unfortunately, they put 2000 on the bottom, okay? So this guy here is on the bottom. So this one here, no, it's not. I get this backwards. Oh, I'm sorry. No, we're right. The range here, no, I get the wrong year here. Give me a second. Yeah, I'm sorry, guys. Unfortunately here, notice that's 90 and that's 94. Okay, so in 2005, it goes to 94. So in 2005, it does go higher. So we're at 94. Okay, I get messed up here. This guy is the pink guy. The guy on top is the blue guy. So 2005 goes all the way to 94. It has a higher max than this guy, which only goes to 90, which is here. All right. Also, the median here is higher for the bottom, right? Somewhere in the mid to high 80s. Here we're in the mid to low 80s. So the median has been pulled over. Now, where do you get these numbers from? Google Sheets will find them for you. Okay. You got your min, you got your max, you got your min, you got your max, you got your median, and then you have all this stuff here. What you notice between these two is this one here, you look at two things. One, this guy especially is much bigger than any other part of the box and whisker. Okay, it's bigger than the first quartile, the second quartile, the third quartile is the fourth quartile. Bigger means more spread out. So that means the year 2000 is going to be probably pulled to the right a bit, and you notice it is pulled to the right a bit. Okay, so you do have this outlier which kind of ruins everything. right? But if we kind of ignore that outlier and just look at this data here, what you have is what looks like a normal curve and then pull to the right, right? And that's what this is. Normal curve, kind of, pull to the right. This one here, a little different. This guy here is slightly pulled to the left, all right? So this one here is pulled to the left a bit or negatively skewed. I don't think it's that much negatively skewed. I think it's more normal. That looks like a normal curve to me. Again, it's not going to be perfect. The only thing that stands out to me is that between the two whiskers in the blue, the left whisker is much shorter than the right whisker. And in that case, that's pulled to the right to me, okay? You're pulling the median over slightly. You're pulling the mean over slightly. But you're going to have this one here is pulling everything over to the right a bit. So this is positively skewed. Okay, look at the difference between these two here. All right, your median in this case is bigger than this. Your range is more, so this data on the bottom is more spread out. You have a lower minimum, you have a higher maximum. That's going to give you a higher range. You have a higher median also. This guy here on the right is skewed to the right. This one here, again, is pretty normal looking. So when we look at these two here, you have this pulled to the right. So this is the same sort of thing, but now these are flipped upside down. I don't know why they keep doing this, but this is the first data first and the second data second. So 2000 versus 2005 in this case. And you notice that this is pulled to the right here. Okay, so that's using Geobra. I don't know how to say that. You can use that to make your box moisture plots. Okay, so when you do have them stacked, you can watch the video. It explains the difference between them, but that's what's going on here. When you have this sort of thing, you can compare not only is this a normal distribution, is this skewed right, but you can compare the two pieces of data. Remember that bigger doesn't mean more, it means more spread out. So there's not more data here, it's just more spread out. There's not more data here, it's just more spread out. One other thing that I didn't say at all yet is what the term we use is called interquartile range. And that is like range. So range is max subtract min. Interquartile range is Q3 subtract Q1. So that's the size of the box in the box and whisker plot. So sometimes we want to know the central data, like the middle 50% of the data. So Q2 and Q3, that's like the core data, I guess. I don't know. Like if you're talking about I don't want to use the word average and middle, but it is kind of the middle data, right? If you look at all the stuff that's in the center, the 50% in the center, 25% above the median, 25% below the median, that's below the median. What's up with that data? Because I might want to deal with that. That's called interquartile range. So in this case, the boxes are about the same size, so the interquartile range would be the same. If you have raw data, so I don't know if we have that anywhere, but if you did have some raw data, all you do is you take your Q3 and subtract your Q1, and that will be interquartile range. Okay, so a little bit different. Take your time with this. You're not going to make them by hand. You're going to get the software to make it for you. Just get used to, pull to the left, normal here. Comparing the two once they're on top of each other, more spread out, bigger range, smaller range, pull to the right here, higher median, lower median. They're good, but they're a little confusing. So hope I helped out a bit. That's box plots, box and whisker plots. Take care.